This is Geology 110. This is our very first lab. And this lab we're actually going to perform an experiment. We're not going to see the results of this experiment until the end of the semester in December. And so over here I've set up the experiment. And so I have 5 stations, each consisting of a hot plate with 600 milliliters of water at 205 degrees Fahrenheit. And what I'm going to do is I'm going to add ammonium phosphate, which is a salt, chemically it's a salt, to the water, stir it until it's completely dissolved. We're then going to allow it to cool and pour the contents of that into this cup. And we're going to allow the solution to evaporate. And in about 6 to 8 weeks to 10 weeks possibly, we're going to actually start to see crystals forming. So what I have set up here today for our lab is 5 different stations. They're all identical. All the burners, the hot plates, are at the same temperature, 205 degrees Celsius. All have the same beakers with 600 milliliters of water. And everything basically is uniform, except there's one thing that varies in this. And the thing that varies here is the amount of the ammonium phosphate. So the ammonium phosphate varies from a lower concentration over here at station number 1, which consists of 300 milliliters. Everything else is the same temperature. Then we go over to station number 2, where the concentration here is 325 milliliters. And there's our salt in the beakers. Station number 3, the concentration here is 350 milliliters. Station number 4, 400 milliliters. And then last, station number 5, at 425 milliliters of the salt. So the concentration, the amount, varies from station 1 to station 5, so station 5 is the greatest. So since there's no students in the lab today, I'm here all by myself. And it's just too bad there's not students here to enjoy this lab. Next semester, everybody gets their shots and the coronavirus goes away. So we're going to employ today the scientific method. And so this is part of the lecture. So the scientific method has 6 steps. The first step of any scientific investigation, scientific method, is an observation. So an observation is something you can see, smell, feel, taste. And after that observation, you're going to form a problem statement. So let's say something simple in your life occurs. You are on your way to go to a store, to school, to a friend's house. You go out in your car, and the car doesn't start. That's the observation. Your car doesn't start. So now you go to the second step, the problem statement. And the problem statement, basically, there's a problem. Your car will not start. You need to figure out why the car doesn't start, because you need to use that vehicle to get to and from school and whatever you have to do. So this is our problem statement. So then we think, okay, the car won't start. We're going to form a hypothesis. And a hypothesis is an educated guess that requires testing. So in the case of your car not starting, you might say, well, gee, maybe I have a bad battery. So you can perform an experiment. You can jump start the car with somebody else's car with jumper cables, or you can take the battery out of the car and take it to O'Reilly or AutoZone or Pep Boys and have them test the battery, and they can tell you if the battery is good or not. So let's say you did that. Let's say you jump started the car and it ran good. You parked it. Next day, same thing happens again. So okay, time to take the battery out. And let's say you took the battery down to the AutoZone or any of the auto parts stores. And they tested the battery and said, no, your battery's good. Wow. Good thing I didn't spend $120 on a new battery. That would have been a waste of money. So you put the battery back in the car and says, gee, what could be wrong now since the battery's not charging? And a little more investigation, you're going to find that that battery it's charged by the alternator. And so you think, well, maybe the alternator's bad. So you can take that out and get it tested. And let's say you take the alternator out. But you notice when you're taking an alternator out that the belt's loose. Wow, could a loose belt cause an alternator not to work? So you take the alternator out, take it down to the auto parts store, they test it and they say, it's good. But I did notice that the belt was loose. And the guy behind the counter says, yeah, a loose belt could do that. So you put the alternator back in the car, you make sure the belt is nice and tight, and now everything's fine. So this is what we do when we basically form a hypothesis. The experiments, taking the battery out, having it tested. Taking an alternator out, having it tested. Observing that the belt is loose, and then when you tighten that belt, the alternator then worked properly. So your first hypothesis that you had a bad battery, upon evaluation of that through the experiment, you would reject that hypothesis. And so since you reject it, you now go back up to hypothesis and you now form a new hypothesis. So your new hypothesis is the alternator is bad. You tested the alternator. It's good. So you reject that hypothesis. Then you come up with another hypothesis, well, maybe it's just a loose belt. So you put the alternator back in, you tighten the belt real tight, and after that the car runs fine, the battery's charged. That hypothesis you accept. And this is how you evaluate. So the evaluation part is you ask the question, did the experiment prove or did it disprove the hypothesis? If it proved it, then we have a theory. And theories are based on the testing of hypotheses. If we reject it, it's no big deal. You just get to go back up and do it all over again. And you can now state a new hypothesis. So we're going to use this process today, and we're going to perform this experiment. So our experiment basically is that we're going to take various concentrations of ammonia phosphate. So there's the chemical formula, NH4, H2PO4. This is ammonium phosphate monobasic. The observation we have here today is that the concentrations of ammonium phosphate vary. There's different concentrations. Everything else is continuous. Everything else is the same. Same water volume at 600 millimeters, same temperature, same room, same time, same day. Everything is exactly equal. The only thing that varies here is the actual concentrations of the ammonium phosphate. So we're going to generate a hypothesis, or maybe even more hypotheses today. And then we're going to do the experiment, mix the solutions, or I'm going to do it. And these crystals will not grow until about 8 to 10 weeks from now. So the purpose of this shows that science sometimes takes time. It's not like on TV, on CSI, where they get the DNA and right away they can go in and get the right suspect and prosecute them and all that. I mean, I'm sure the police wish it worked that well, but it doesn't in reality. Science takes a lot of time, a lot of experiments. And science doesn't happen overnight. So we're not going to be able to evaluate our result of our experiment until December. That's going to be our last and final lab. So the last lab in December is we're going to evaluate this experiment. And at that point in time, we're going to see if our hypothesis stood up. So we're going to do the evaluation part. We're going to ask ourselves, are we going to accept or reject our hypothesis? And we may come up with one hypothesis, we might come up with 3. And this is what you're going to have to do as a class. So this recorded part of the lab will be paused, and I'm going to ask you to come up with hypotheses. We're then going to put those hypotheses in Canvas, and you're going to go in and mark true or false if these are our hypotheses. So that's going to be the quiz for the first week. Pretty simple. So what I'm going to do is I'm going to over here, and I'm going to do the experiment. I'm going to pause the camera, unless you really have nothing better to do and sit and watch me for the next half hour stir a bunch of beakers with ammonium phosphate. And then I'm going to add some food coloring to just give them some little coloring effect. And so we'll be back in just a few minutes. All right, we're back. 45 minutes later, I stirred all the solutions, emptied the ammonium phosphate into the water, stirred it vigorously, and there's a little bit of precipitate beginning to form at the bottom, and that's actually good because that's going to provide us with a base where the crystals are going to grow. So everything's pretty much dissolved. Interesting observation here is that the higher concentrations of ammonium phosphate seem to have a little bit more of a precipitate at the bottom. So we might want to talk about this as a possible outcome variant, that maybe a base may provide a good crystal. So I'm basically taking all of these beakers and I'm pouring them in. So what I did, I add a little bit of food coloring. So I made sure that the food coloring was basically the same volume in each one of these. And if you notice, I'll pour this back into the beaker, that the food coloring concentration isn't so much that I think it's going to interfere with the growth of crystals. I have found that in the past that sometimes that is a problem, that if you have too much food coloring, that it actually interferes with the growth of the crystals. So basically I'm doing this for every one of these. Different colors. So you have a yellow, a red, a green. How about that? Green and red together. Considering we're going to evaluate this in December, right near Christmas. So good Christmas colors. This one here is the best color of all. That's my bias, a blue. And I'm going to let the rest of this precipitate out. I'm just going to go ahead and keep pouring the water back and forth until everything is in the jar. And then I mixed red and blue together here. To make a kind of strange color here. Kind of a brown color. Almost like a smoky color. And so we're going to form a hypothesis based on the different concentrations of this ammonium phosphate. So here, there's a little bit of precipitate left in here. I'm going to make sure that it does wind up back into the solution by pouring back and forth until all of the material has been removed. So I'm not going to bother you with going through that process. But just to recap, what we're going to do now is we're going to come up with a hypothesis. And like I said, we're not going to be able to test that hypothesis until the very last lab in December, because these crystals are going to require a considerable amount of time to grow. Between 8 and 10 weeks. It really depends on the temperature of the room. If it gets cold out and they put on the heat, that speeds things up. If the warmer room, more evaporation, crystals grow a little bit quicker. So we're going to actually generate our hypothesis, and then we're going to actually perform the evaluation part. So today we did the observation. The observation is various concentrations of ammonium phosphate. Problem statement, we want to see what the impact is going to be on crystal growth. So today we're going to conclude this class by forming a hypothesis. The experiment has been completed. Now we just have to allow those crystals to grow. So our part's done. We have to let nature take over from this point, and we'll see how well those crystals grow. And then when we return to this at our very last lab, we're going to look at the evaluation. And we're going to look at our hypotheses that we generate today. The last class, we're going to look at those hypotheses, and we're going to accept all of them, or some of them, reject some of them, or reject them all. We'll see how it goes. And at that point, we're going to have a theory on crystal growth. So that concludes lab number 1 for Geology 110 live online for the fall of 2021.